Today we'll discuss the magnetic force on a magnetic dipole. We'll consider the specific case where a falling magnet experiences a magnetic force due to the magnetic field generated by an induced current in a loop. We recall in an earlier lecture that as a magnet falls, oriented as shown, it can induce a conventional current, capital I, in a wire loop that, in turn, produces a magnetic field, vector B loop, as shown. We also learned earlier that both the bar magnet and the current loop are magnetic dipoles, each of which can be characterized by vector magnetic dipole moments. So, for the magnet oriented as shown, the corresponding dipole moment, vector mu sub m, looks like this, pointed from the south pole to the north pole of the magnet. And for the current loop oriented as shown, the corresponding dipole moment, vector mu loop, is oriented as shown. Now the central question we will address in this lecture is, what's the force on the falling magnet due to the current induced in the wire loop? Let's call that force F loop on M, where M stands for the magnet. We can get a quick qualitative answer to this question by doing the following thought experiment. Imagine we replaced the current loop with a second magnet with the same vector dipole moment, vector mu loop. The imaginary second magnet would have to be oriented as shown, with the north pole above the south pole. Now that means the two magnets have the same kind of pole, north in this case, pointed toward each other. So the force on the top magnet, the falling magnet, would have to be pointed upward. Let's see if we can make this picture quantitative by talking through the actual calculation of vector F loop on M. Here's how that goes. We start with our falling magnet with vector mu sub m, the dipole moment oriented as shown, and with the velocity of the falling magnet, vector v, represented by an arrow pointed downward in the falling direction, which we'll take to be the y-axis. Now on the dipole axis, parallel to the y-axis, we consider a circular area shown as a shaded region that is perpendicular to and centered on the dipole's axis. The circular shaded region has a radius which we'll represent by the Greek letter rho. Now we know from an earlier lab that we can describe the bar magnet's field with this expression, where vector r represents the observation location for the magnet's field, and the coordinate y represents the distance from the magnet to the shaded area. Note that the shaded area doesn't move. It's fixed in space. Now we know that we can use our expression for vector b sub m to find the magnetic field on the shaded area. And in actuality, as shown, that field does vary in space, something like that shown by the black arrows. Now, knowing this field, we know we can compute the magnetic flux on that shaded surface. Moreover, we know as the magnet falls, that flux is changing in time. So the time derivative of the flux on the shaded surface can be calculated by doing the flux integral and then taking a time derivative. We won't show the details here. We'll just show here the final result for the magnitude of the time derivative of the flux on the shaded area. Now we know from Faraday's law this is the EMF, the magnitude of the integral of the curly E field around the closed path bounding the shaded area. Now if we have a wire loop that follows this path, we know that an induced conventional current, capital I, will arise. We can find I knowing the resistance, capital R, and the EMF, which we just stated on the last slide. I will just then be the EMF divided by capital R. Now at the location of the current loop, we know vector B sub m, the magnetic field of the falling magnet, is acting. And we can use our expression for vector B sub m to find the magnetic field for all observation locations on the current loop. We also know that both I and vector B sub m will produce a magnetic force, F, on a short piece of the wire loop described by vector delta L at a given location on the wire loop. If we think a bit about this, we'll notice that vector B sub m and vector delta L are perpendicular to one another, so that the magnitude of F is just the product of I times the magnitudes of vectors delta L and B sub m. Using the right-hand rule for cross products, we can see that vector F must point something like this at the particular observation location shown. Now notice that vector B sub m has the same magnitude everywhere on the loop, but is pointed in different directions. However, note that on opposite sides of the loop, vector B sub m has the same y components, but x and z components of opposite signs. That means for forces, we only need to pay attention to the y component. B sub m makes an angle of theta with the y-axis everywhere on the loop, which means the force makes an angle of 90 degrees minus theta with the y-axis. So the magnitude of the y component of vector F is just F cosine 90 minus theta, which is just F sine theta, where sine theta can be found by taking the magnitude of the cross products of the unit vectors for mu sub m and B sub m. Now, since all the y components of F are the same everywhere on the loop, we can find the total force on the loop by replacing delta L with the circumference of the total loop and inserting just the y component of B sub m on the loop. We end up with this result, which means all we need to do is compute B sub m at one location on the loop, compute sine theta, and plug these in to find the total force on the entire loop. Note that all the y components point downward, so the total force on the loop, vector F on loop, points downward. We can now find the force of the current loop on the falling magnet. It's given by Newton's third law, which says the force of the loop on the magnet must be pointed oppositely to the force of the magnet on the loop. So that means vector F loop on M, the magnet, must point upward, just as we found from our earlier qualitative argument. Additionally, by Newton's third law, these two different but related forces must have the same magnitude. Now let's push this one step further. Let's use our knowledge of all the forces on the falling magnet to predict the motion of the magnet using what we remember from Physics 1, our knowledge about mechanics. Let's assume that the magnet has mass capital M and is at position vector r sub m when we start to make motion predictions. In addition to the magnetic force F loop on M, we know that there is a weight force, the force of the Earth's gravity acting on the falling magnet. Call that force vector capital W, which we know points downward with constant magnitude, capital M times g, the acceleration of gravity. So the total force, the net force on the magnet, ignoring air drag, is the sum of these two forces. Knowing this, we can predict the magnet's falling velocity, v final, a little later in time, delta t, starting from an initial velocity vector, v initial. This is just Newton's second law. After making this prediction of the final velocity, we can use this to predict a new position for the magnet a small time delta t later. That's just vector r sub m initial plus vector v final times delta t. We can just iterate these equations repeatedly on a computer to predict the motion of the magnet. That's in fact what you will be doing in the upcoming lab, where you will make observations and motion predictions of a magnet falling through a conducting tube, where the tube is a roll of aluminum foil from your kitchen. We will use all the ideas discussed in this lecture to build a computer model that predicts the motion of the falling magnet, specifically predicting the time it takes for the magnet to fall through the conducting tube. Now, to model the tube, we will use several conducting rings, all centered on the dipole axis of the falling magnet. We'll compute the magnetic force of each ring on the magnet and add them up using superposition to get the force of the conducting tube on the magnet. That's it for this lecture. In our next lecture, we'll discuss some examples with Faraday's law involving coils of conducting wire.